Hello, everyone. My name is Illaria Caiazzo. I'm a postdoc at Caltech, and I'm very happy to tell you today about the work that we have been doing with the ZTF variable stars group about white dwarfs, and in particular about our search for white dwarf merger remnants. So as you all know, white dwarfs are the most common stellar corpses. All the stars with a mass up to about 8 or 9 solar masses are become white dwarfs at the end of their lives. So more than 97% of all stars are bound to become white dwarfs at some point. And you surely know about the white dwarfs, but I'm just going to tell you briefly about the typical white dwarf is, as a mass of about half the mass of the sun, 0.6 the mass of the sun, and a size that is about that of the Earth or a bit bigger. And it has this stratified interior in which you have a core that is made of mostly carbon and oxygen, and an atmosphere that is stratified helium and almost pure hydrogen at the surface. And indeed, here you can see the typical spectrum of a white dwarf only shows hydrogen. High hydrogen absorption feature here, for example, is the Balmer series in the optical. And so we know a lot about white dwarfs, and especially about these typical white dwarfs, but there are a lot of white dwarfs that are atypical. For example, more massive white dwarfs have actually different composition in the core, is mostly oxygen, neon, magnesium. Or for example, there are a lot of white dwarfs that have different composition on the surface. And those are the ones that are more puzzling, and there's a lot of open question about the atypical ones. And my favorite type of atypical white dwarfs are the ones that are magnetic. So they're not that rare. They're about 20% of white dwarfs happen to be magnetic. And we have seen a huge range of magnetic field strengths on white dwarfs. They go from a few thousands of Gauss to up to almost a billion Gauss, so a billion times, for example, the magnetic field of the Earth. And we still do not know why some white dwarfs are magnetic and some white dwarfs aren't, or where this huge diversity in magnetic field strengths come from. And there's several theories, several possible explanations, and they are divided in two main families, let's say. One that ties the magnetic field to the evolution of the white dwarf. For example, the progenitor star could have been magnetic, or the magnetic field could have been made during some processes before the white dwarf was actually born as a white dwarf. Or the other family ties the magnetic field to interactions. For example, if the white dwarf underwent some very strong accretion phases, or if it's a product of the merger of two white dwarfs. In this case, this very strong dynamo that arise in these processes can create very strong magnetic fields. Now, several of these processes can be at play in different white dwarfs. And the one that I will focus more in this talk is about the mergers of two white dwarfs. But how do we find white dwarf mergers, and how do we find white dwarf? So before Gaia, it was very hard to actually find white dwarfs and identify white dwarfs. So white dwarfs are, the easiest way was through spectroscopy, to get a spectrum to figure out if a star is actually a white dwarf. And indeed, most of the white dwarfs before Gaia were identified with the Sloan digital survey, which is this survey that took spectra of many, many, many stars, and some of them happened to be white dwarfs. Or if you knew the distance to the white dwarf through reduced proper motions, or because, for example, the white dwarf was in a cluster, and so you know the distance because of that. And then from photometry, in that case, you can recognize the white dwarfs. But after Gaia, things have changed a lot, because Gaia, if you don't know, it's this amazing telescope that measured very precise photometry and astrometry for billions of stars. So for billions of stars, we have the color, the luminosity, and the distance. And so thanks to this, we can plot, as you can see here on the right, an HR diagram with an absolute magnitude on the y-axis because we know the distance. And so in this way, the white dwarfs are very easy to be identified photometrically because they are this blob here on the lower left corner of the plot. And so of course there are contaminations, but here you can see before Gaia, we knew about 35,000 white dwarfs, mostly in the northern sky, because that's where the Sloan Digital Survey took data. And it was mostly, the most brightest, the most bright, again, not a very uniform sample. But here it's after Gaia DR2, we, got 260,000 white dwarfs. And after the early data release 3, this sample even doubled to 400,000, so a much uniform, much deeper sample. So this is actually a great moment to study white dwarfs, thanks to all this amazing data. But this is just for normal white dwarfs. But how do you find then a merger remnant, a white dwarf that is the remnant of the merger of two other white dwarfs? Of course, I already said highly magnetized because of the strong dynamos that arise during the mergers. Massive, because if you take two white dwarfs and the result either explodes in a supernova, if the mass is higher than the Chandrasekhar mass, or it becomes a white dwarf, which you expect still it's going to be more massive on average than normal white dwarfs. And one thing that I haven't mentioned is that it has to be rapidly rotating, because if you have two white dwarfs in a binary that merge, some of the angular momentum of the orbital angular momentum of that binary has to be conserved in the final product. And here there's a study that's been published this year by Josiah Schwab that actually studied what kind of periods do we expect for the rotation of a merger remnant. And of course, the merger remnant, as soon as it's born, is actually rotating very, very, very fast, with periods of less than a minute. But since some of this angular momentum is lost when the merger expands, because it's burning, nuclear burning carbon a lot. And so in this expansion, it loses a lot of angular momentum through mass loss. And at the end, the white dwarf remnant, we expect it to be rotating on periods of an order of minutes, 10 minutes, 20 minutes, up to an hour or so. And so the ZTF in this sense is an amazing tool to find merger remnants, because merger remnants can be photometrically variable. The luminosity can change, because if you have a very strong magnetic field on the surface of a white dwarf, then the emission is not uniform. You can have bright spots, you can have dark spots, you can have temperature gradients because of the magnetic field. And so as the star rotates and these spots come in and out of the line of sight, we see the luminosity changing. And of course, by now you all know about ZTF, and you know that it's called ZT Transient Facility to look at transient phenomena like supernovae, etc. But it's also an amazing variable facility to look for variable stars, because it has this huge field of view that takes an image of all the northern sky every couple of nights. And so you can very quickly get hundreds of these images, and each star in that image will have a photometric measurement. And so you get this database of photometric measurements, and so you can look for objects that vary in luminosity, and in particular to objects that vary periodically for the white dwarfs, as they rotate, we expect to find luminosity to vary over the period of the white dwarf. And of course, we do that using some amazing software that has been developed by people in the variable stars group. And this is our search. Of course, as I said, we want to look for massive objects. So here, again, this is the Gaia HR diagram. We know that the most massive white dwarfs are located in this area, so below the main white dwarf track. So they're very blue and faint objects. And we looked inside the ZTF database for this type of white dwarfs that have very small periods, from a few minutes up to a few hours. And here is an example of the light curve of one of these objects. This light curve, so all of these, so how the photometry varies with time, it's been phase folded. So around the period of the white dwarf, that is in this case is about half an hour. And you can see here it's showing 2 periods, and you can see that the luminosity varies and it has 2 differential maxima. And so we found a lot of these objects that had very small periods and were very massive white dwarfs, but to understand where the variability was coming from, we really need a spectra. Because of course, white dwarfs can vary also for other reasons. For example, some white dwarfs pulsate, and that's why we see this variation in photometry. So what do we expect when we look for white dwarf magnetic spectra? I showed you at the beginning what a normal white dwarf spectrum looks like with all the lines of hydrogen. Well, when you have a magnetic field, here you can see again the lines of hydrogen, they're about in the same position for low magnetic fields, but each line is splitted in 3, as you can see. That is because the magnetic field lifts the degeneracy, the energy levels inside the hydrogen atom. And so each level gets splitted in 3. This is called Zeeman splitting. And so you can see that as the higher the field, the farther away the Zeeman components become. So here for white dwarfs with this kind of fields, that's how you identify the magnetic field. But as you can see that as the field becomes higher and higher, these are other white dwarfs with higher fields, you don't see this triplet structure anymore. It becomes more complicated. And that is because, as you can see here, this is again, these are 3 hydrogen lines, and where is the position of the line, so H, beta, gamma, and delta, and where is the position of the line in wavelength as the field changes. And as you can see, at low fields, around 1 billion Gauss, you have these triplets, but as you go to higher and higher field, these triplet gets split in even more components, and each component gets shifted very quickly with the field. And that's why it becomes much harder for higher field to actually identify the field, because if you imagine this component, since on the surface of a white dwarf, the field doesn't have only one value, it changes. You might have dipolar structure or even more complicated. When you sum the light from the entire surface, you're actually looking at different field strengths. And that's why often absorption feature get washed out. So the way that we actually identify white dwarfs with very high magnetic fields is by looking at this type of components of the hydrogen lines. They're called stationary, and that's because at some values of the field, they reach either a minimum or a maximum in wavelength or energy, depending on what you're looking at. And so you can see as the field changes, the position of the line doesn't change very much, and in this way it doesn't get washed out. And so here, for example, you can see these spaghetti plots here. It's exactly the same thing that I was showing here. And these are different white dwarfs with different fields. And what we do is that we try to identify these very strange absorption features with the actual features of hydrogen at a determinate field strength. And so here are some examples of the objects that we found and what the spectra look like. For example, here on the upper left, you can see this object has a period of about 20 minutes, and it's very massive, about 1.2 solar masses, so very good candidate for a merger remnant. And on top of that, we find that the field, you can see again, this spaghetti plot can be identified to be 175 megagauss, so pretty high field. And here, other example is a beautiful 105 megagauss. You can see all these lines, they're very strong, and they're all at about 105 megagauss here in the spaghetti plot. So this is the kind of objects that we are finding. It's very exciting because we're finding many more of these high magnetic field white dwarfs that are known. And there's not only hydrogen, the ones that I was showing was mostly hydrogen, but this one, for example, has a helium atmosphere, and so the lines appear maybe even more weird. These are all helium lines in high magnetic field. This one is a carbon white dwarf, carbon-dominated atmosphere, etc., etc. So many interesting objects, and all finding and studying them. But I just want to spend a couple of minutes telling you about maybe the most extreme object that we found for now, which is ZTF 1901 plus 1458. This is the it's the smallest white dwarf that we know of. And since white dwarf become smaller when they're more massive, this is also the most massive white dwarf known. It's very close to the Chandrasekhar limit. And we found it thanks to ZTF. And because it really caught our interest immediately, because it has only a 7-minute period. You can see here the light curve. This is the ZTF light curve that you're going to play with in one of the Jupyter notebook to actually find this 7-minute period. And here you can see again the Gaia CMD, and you can see that the white dwarf down here is extremely blue, which really tells you that the white dwarf is very massive and hot. And here is again a pan-star image of this white dwarf. And so we found these 7-minute periods. We saw that the white dwarfs looked very massive. And so what we did is that we followed it up. So we took a spectrum with Eldris on Keck at Mauna Kea. And so you can see again the spaghetti plot, and we were able to identify the field to be about 800 megagauss, which is one of the highest field ever found on a white dwarf. So it's extremely magnetized. And then we got some more photometric observation. There was already available photometric observation from pan-stars, which you can see here in blue. And then we requested some ultraviolet observation from Swift. And so from this observation, we were able to constrain the temperature of the white dwarf and the radius. So it's very hot white dwarf, about 50,000 degrees. So also very young and very small. The radius is about 2,100 kilometers. And I told you at the very beginning, the typical white dwarfs have a radius that is about that of the Earth, or even a bit bigger, about 7,000, 8,000 kilometers. This white dwarf has the radius that is much more similar to that of the Moon. As you can see here in this artistic image of ZTF 1901 compared to our Moon, is really close to the Moon radius. And since, as I said, since small radius means large mass, the mass of this white dwarf is the closest to the Chandrasekhar that we know of. And of course, it depends on the composition. We don't know what's made of in the core, but it's probably between 1.33 and 1.37 solar masses. And so being the white dwarf so massive and so small, it's extremely dense in its core. And so what's happening, there's a phenomenon happening in its core, that something that really only happens in young neutron stars. It's called inverse beta decay. It's something that happens at very high density. And so we have sodium nuclei that are capturing electrons and so transforming into neon. And this is extremely interesting because this is the only white dwarf known that is so dense that something like this could be happening in its core. And also because this process releases a lot more neutrinos that normal neutrino processes in white dwarf. And this process is called Urca, and it's really dominating the neutrino cooling of this particular white dwarf. And so it's gonna cool very fast, and it's gonna, and since, you know, this inverse beta decay, this electron capture, is removing electrons from the core of the white dwarf. But electrons are the ones providing the pressure to the white dwarf to withstand its own self-gravity, because white dwarfs, contrary to normal stars, they're not kept up by nuclear burning, they're kept up by electron degeneracy pressure. And so if you remove electrons, the white dwarfs will keep shrinking. And so we don't know what's going to happen. It might freeze, and so this process will stop because the core will become solid. Or if it continues for long enough, and if enough electrons are removed from the core of the white dwarf in about a few 100 million years, the white dwarf might become unstable and collapse. Of course, this is very speculative. We don't know if that's going to happen, but if it does, then, you know, it's very interesting, because this is a white dwarf that is the product of a merger that barely avoided explosion. It barely avoided exploding in a supernova because it was just not massive enough. But it might meet that fate in the future and actually explode. Or depending on the timescales of oxygen burning, it might actually not explode, but collapse into a neutron star. That is also would be maybe even more interesting, because it would be a different way to create neutron star just from an isolated white dwarf. And again, we don't know if this is going to happen, but if it does, it's very, very interesting also, because this object is not a rare object, because we found it only at 40 parsecs away from Earth. It's a very close star, so it cannot be a very rare type of object. And so I'm way above my time limit, so I'm just going to leave you with this slide. I told you about one particular object that we found. It was very interesting per se, but I think the most interesting results of this search will come from the samples, so from having a big sample of white dwarfs that we know came from mergers, because it will help us understanding the merger remnants and their properties. So what they're made of, do they evolve differently from normal white dwarfs? How long does it take from you know, the actual binary, white dwarf binary, to merge and create these remnants? And then of course we will be able to find the rate of white dwarf mergers in the galaxy just below the Chandrasekhar mass. And then we can ask ourselves, how does this compare to the type 1a supernova rate? Like, is it comparable? Can the supernova type 1a be the same? And then last but not least, understanding the magnetic field. As I started, finding all of these magnetic merger remnants can tell us about, you know, are really the magnetic fields the results of the mergers? How does the field affect the spectra of these white dwarfs? So I'm going to stop here, and I'd like to thank you very much for your attention, and I hope you'll have fun in this school. And please email me if you have any questions. Thank you very much.